the... Okay. Oh, hang on. It just came up for some reason. I don't know why. Oh, you did that, did you? Okay. All right, thank you very much. Okay, terrific. Thanks. Bye. All right, you want to hold it down? There. Had to do something remotely to get it to talk, which is weird. Who didn't show up yesterday? Raise your hand. A few of you. All right, I know these three of you have some kind of conflict with work. You need to do your very best to look at what was done in the previous lecture. One of you said you couldn't get the visual. Whoever that was, has anybody seen if the visuals mounted up on the university site? Anybody looked? Wasn't there? All right, well, it's beyond my control. All I do is what I do here. It's in the university's hands after that. Anyway, you want to do your best not to miss a lecture because you're automatically behind. And I move very quickly in this class because I need to cover a lot of territory. So do that. Try not to miss a class because you may say, I can just get it from the university site. But there's a very big difference in how your brain operates when you look at something on the screen as opposed to doing it live. See if I turn these lights down, huh? Okay. So if I'm lucky, nothing's going to go weird today. And yesterday we had 2 hours of enthralling lecture material, beginning phase diagrams, binary phase diagrams. And we learned some fundamental terminology and some fundamental issues. What did we call this kind of diagram? Yeah, it's a binary. It is a simple eutectic. Where's the eutectic? Where's the eutectic? We're going to have to pick on people? Tell me where in the diagram it is. Sorry? Where the three lines meet. It's at the bottom of the V. It's where the three lines meet. It's the lowest part of the curve. It's in the middle of the diagram. There's various ways to do it. This is the eutectic. What is this? And this? Of? All right. So those three things are known as what? Invariant points. Okay? If I have a diagram that looks like this, what do I have? What kind of partial solubility do I have? Mutual. They're both soluble in each other. Right? A is soluble in B, B is soluble in A to a certain extent. If I have a diagram that looks like this, what do I have? Complete solid solubility. What do I have here? What phase or phases? A liquid. How do you know? How do you know that's a liquid? He says it's above the melting point. This is a good example of something you need to avoid. Melting points are virtually irrelevant. Melting points are invariant points. They're unique to each compound or element that we have. So it's not above the melting point, is it? Above what? Above the liquidus surface, or the liquidus curves, or the liquidus lines. That's how we know it's a liquid. It is above the liquid. What's that horizontal line called? The solidus. And below the solidus we have all solids. Above the liquidus we have liquid. Okay? What do I have in here? L plus. We'll call that solid solution beta and that alpha. If you say L plus B, you are wrong. B is stoichiometric. It's on the vertical line. It is the end member. Okay? Beta is the solid solution. So this is L plus beta. What's in the other triangle? Alpha plus liquid. And what's down here in the rectangle? What's in here? Solid solution. What's here? And in here? Okay, so those were the two main types of diagrams we looked at. We had a simple binary with a eutectic or an invariant point present, and we had a solid solution. Complete solid solution, and we had maximal, minimal, ascending, and descending. We also learned that we can have an intermediate phase that forms, and if the diagram looks like this, what is the nature of that intermediate phase, AB? What is it? What do we describe AB as? It is, begins with C, compatible. Oh, it's not compatible. What is it? Congruently melting. What does congruently melting mean? He says it goes from solid to liquid and there's no what? What doesn't change? The composition. No change in composition. It's a melting point. Okay, that's what we know as a melting point. That's a congruently melting intermediate phase. But if I have a diagram that looks like this, then when AB is heated up to what temperature? The paratectic temperature. What happens to it? Does it melt congruently? What does it do? Huh? What does it do? And what do we call that? Or we also call it incongruent melting. Okay, it melts incongruently. It doesn't go from a solid to a liquid of the same composition. It goes from a solid to a solid and a liquid of different compositions. That's incongruent melting. It's also paratectic decomposition. All right, so we have an intermediate phase, and I can define it any way I want. But if it's on the edge of a diagram, if it's an end member, I have to make it congruently melting. If I don't, I will have a quasi-binary, quasi-ternary, or pseudo-binary or pseudo-ternary phase diagram. not a true one. Okay, so we have these guys that can happen. And if I have AB sitting in the middle of A and B, what does that say about A and B? Sorry? They're incompatible. They don't like each other and they react to form AB. If I do not have A and B, sorry, how about A and AB? What are they? A and AB, what are they? They don't react. What are they? They're compatible. A, B, and B are compatible. A and B are not. They react to form AB. All right? That's a recap of yesterday's lecture. Who actually went home and looked at their notes for 5 minutes? Raise your hand. All right, not too bad. The rest of you lazy sods, give it a go. You cannot cram right before the final in this class. If you think you can, sorry, I'll probably see you next year. You cannot cram. There's nothing to memorize. You do not memorize anything in this class. Nothing. Zero, zip, nix, nada, nothing. And those of you who are used to doing that are used to cramming for the exams. It's not going to work in here. You need to know how to interpret these diagrams. You have to learn it along the way. And the good thing is, if you do, you don't have to study for the final exam because there's nothing to study. You already know it. So your life becomes easy. But most of you are in this mindset that you can cram it and memorize it and you're going to make it through. It doesn't work in this class. So spend a few minutes each night and try to get it to sink into your neurons, and you might actually manage to remember it. How many intermediate phases do I have now? 2? So if I put A and B together, what are my possible phase assemblages after equilibration? What are my possible phase assemblages? I put A and B together as powders, shove them in a furnace, react them. What might I get? I'm not telling you the composition, so I'm leaving that open. Come on. I told you this yesterday. What are my reaction products? Okay. Turquoise switch. What are my reaction products? My potential reaction products in that system. AB. AB. That's correct. A2B and AB2. Those are my two potential reaction products. But my question was, what are the potential phase assemblages? Okay? You in the earth-colored shirt. What are the potential phase assemblages? Well, that's possible, but not at room temperature, because when I ask for a phase assemblage, I'm implying what you find when you analyze it. Alpha? Where did alpha come from? Is there a solid solution there? No. So we won't have alpha. So, what do you reckon? Sorry, say it again? A2B and AB2. Okay, that's correct. That's one of them. How about the rest of them? You just quoted me a composition right here. Right? What's on the sides is what's in. So what are the other two? Well, yeah, you could be right on the line. That's correct. We did that yesterday. So there's A2B. So that's one. What else? AB2. Well, that's a no-brainer. And no, other than that. Anyway. So, okay. You. What are the other two answers? A plus A2B. Right? Now, don't congratulate yourself. I'll find some way to embarrass you. What's the other one? Okay. Right there. That's obvious, isn't it? You're either in between the lines or you're on the lines. And there's 5 answers for potential phase assemblages. So if I take this thing and I equilibrate it, and then I analyze it in an X-ray diffractometer or a Raman, that's what I'm going to find. Okay, that's at room temperature. Now, I'm going to make these congruently melting. So both of these intermediate phases are congruently melting, and I can pick out their melting points by picking the temperature right here. So, how many invariant points do I have in this phase diagram? Okay, guy with his finger pointing right there, he's obviously working out the answer. What is it? How many are there? 7. Let's put that to the test, huh? 1, 2, 3, 4, 5, 6, 7. Good. Okay, so we're going pretty well, getting answers pretty readily, which suggests to me that some of you are getting it. Hopefully, most or all of you are getting it. So if I were to take a slab of A and a slab of B and put them up against each other, and then put them in a furnace and equilibrate them, I could get some strange things happening. There's 2 potential reactions. Now remember, when you put 2 solids together like that, you do not have a composition. You don't know what the composition is. You have an infinite supply of A and an infinite supply of B, and they happen to be in contact. What actually happens is what people used to do in the old days when the equipment was really primitive. They'd actually watch A and B diffuse into each other, and then they'd polish the microstructure, and they could actually pick out the locations of the different phases. And they could analyze the phase diagram from the microstructure. So in this case, you'd have 2 slabs that were in contact, and at the end of the process, you'd have a layer of A2B and a layer of AB2, and they'd be shifted somewhere, and that would tell you those were your reaction products. And they're actually located in the middle of the diagram because diffusion has to go one way and then the other way for the other element, and as they cross, they react, and they form these phases. So you'd actually be able to draw a phase diagram just from the microstructure. And we still use that principle when we analyze microstructures, when we're trying to figure out what happened to a material that's gone bad or good or whatever. All right, so we have lots of possibilities here for intermediate phases, and there are systems with 6, 7 compounds that can form. Trying to get this thing to go black, but it doesn't seem to want to give me the option.
Oh, you just have to.
There we are. Right. So I've got this intermediate phase AB. And I heat it up to T1. And I've got a horizontal line that cuts across the diagram. What happened? Let's label the phase fields. What's up on top of the diagram? Okay, what's in the left-hand triangle? What's in the right-hand triangle? What's in the rectangle underneath? How do you know? It's what's on the two sides of it. So this is A plus B, which is kind of weird because that's what I started out with, isn't it? But before that, what's on the left-hand square? Okay, so the intermediate phase AB formed, we heat it up, and at some temperature, everything changed. What happened to AB? It decomposed. It decomposed as I heated it upwards. So we can call that an upward decomposition. Begin with, but it's actually got another name too. Now, if you remember, a paratectic decomposition reaction upon heating was solid 1 goes to solid 2 plus liquid 3, right? That was a paratectic reaction upon heating. Now this one, this phase diagram here, starts with a solid, and we're heating it. So that's heat. And that goes to form solid 2 plus solid 3, doesn't it? So what this is an all-solid analog of a paratectic reaction. And when we have that all-solid analog, we make it an oid. That is a paratectoid reaction. It's easy to remember these names because it's not an issue of memorization. It's an issue of logic. If you know what a paratectic and a eutectic are, which are totally fundamental, and you remember that the oids are all solid analogs, then you're going to remember paratectoid. We must have a eutectoid as well, don't we? Okay, so now you got another invariant point. Which one you call it, I don't care. They're both correct. All right. Upward decomposition or paratectoid, either one. All right? So now you know melting points, paratectic, eutectic, and paratectoid. Here's another phase diagram, and AB is solid 1 upon cooling goes to solid 2 plus solid 3. And as you know, a eutectic is upon cooling, liquid 1 goes to solid 1 plus solid 2. So this is a eutectic, and this is a eutectoid. Okay? Totally logical. Yeah. It's just the way people chose to do this. I'll give you a little bit of the history of how all this happened. You guys have all heard of J. Willard Gibbs, American guy who made thermodynamics what it is today. Gibbs free energy, right? You heard of the name, right? Okay, he was an American, and he worked in the East Coast, I don't remember what university, and he published in 1872 3 papers. Each one was the size of a book. I've seen them. They're all octavos and about this fat. And he laid down the rules of thermodynamics in those books. Problem was nobody understood what the heck he was doing. And the books just languished. But Gibbs always had great confidence in what he had done, and he had produced something of real significance. But nothing ever happened. It was too difficult. In the first decade of the 20th century, there was a group of Dutch scientists who took Gibbs's concepts and turned them into graphical representations. The leader of the group was named Schrijnemacher. And they published a 6-volume set of books, which I have, in Dutch, on how to turn Gibbs's weird words into graphical form. And once they published those books, that absolutely galvanized the scientific world. And in the 1920s, there was a flowering of books on phase equilibrium because they saw what you could do with these diagrams. It was no longer this horrendous thermodynamics calculating enthalpies and entropies and free energies and what have you. None of that nonsense. We can turn them into graphs. And we're visual creatures, so we respond better to visual stimuli than to words. Some people's linguistic centers in their brains are better developed, so they actually respond better to words, but most people respond very strongly to visual stimuli, and that's why our eyes are so highly developed, and our optic nerve leads to a very big part of our brain processing signals. So once that happened, all of the scientific world recognized how useful it could be. And so it all depended on turning Gibbs's words into images. And that's what this class is about. I'm not interested in calculating these things. You can calculate phase diagrams very easily with thermodynamics, with today's software packages, very advanced, but in those days it was all done manually. So that's a bit of a sidestep. So now we have eutectics, paratectics, melting points, paratectoids, eutectoids. Yes?
The eutectoid reaction should that be S1 to S2 plus S3?
Yes, did I get that wrong?
S3.
Yes, S3. Yes, thanks. Okay. Now, we obviously are going to have some more invariant points to worry about. So I now got a new kind of horizontal line here. Let's label these phase fields. What do I have up top? Okay. And what's in here? What's in this triangle on the left? What's on the sides? Say plus liquid. What's in this little triangle next to it? And the wedge next to it, or the triangle, whatever, next to it? Same thing. And the last triangle? Alpha. Somebody say alpha? There's no solid solutions in this diagram. No Greek letters. What's in the little rectangle on the lower right? What is it? Okay, AB plus B. What about the little rectangle on the left top? Sorry? What is it? And what's on the last rectangle? Huh? What is it? Anybody see some problem in the logic here? How can I have two phase fields with the same name? This is stupid. If that's the case, why would I draw a line between them? Somebody got a flash of inspiration here? Crystallographic phase transformation. What's that? Same material but different crystal structure, as in FCC to BCC. That's what a metallurgist would say. A ceramic engineer would never say BCC. Cubic, dragon, hexagonal, trigonal, rhombohedral. No, it's not crystal structure. Monoclinic to triclinic, whatever. Different crystal structure. So that must mean that's alpha A, and that's beta A, and this temperature right here is a crystallographic phase transformation. A number of years ago, I had a student, he's a bit of a smartass in the class, and I was doing this stuff, and I wrote CFT. So he raises his hand and says, "Excuse me, why did you write CFT?" And I said, "Because I like it and you can tuck off." And of course the whole class burst out laughing, and everybody remembered what a CPT was after that. Okay, CPT, crystallographic phase transformation. See, lots of those. And you'll notice that it's A that is undergoing the crystallographic phase transformation, right? And we know that because it's on the left-hand side of the diagram. That's one of the end members of that phase assemblage, of the geometric shape. So here's the variation. What have I got going on here? Anybody have a flash of inspiration here? What have I just drawn? Anybody know? Anybody want to have a guess? I won't make fun of you. Nobody wants to have a guess. All right, let's label the phase fields then. What have I got in the lower left rectangle? What is it? Lower left rectangle. Somebody would like to say it clearly and crisply? And loudly? What is it? Alpha? There's no solid solutions in here. There's no alpha. Solid solution has a homogeneity region. These are all lines. Don't suggest solid solutions unless you see them. So, what do I have in the rectangle? A and AB. So what's in the rectangle right above that? A and AB. So the lower right rectangle, what do I have? And above that? So there are two possibilities here. One possibility is that A and B undergo a crystallographic phase transformation at exactly the same temperature. And do you know the odds of that? Infinity. There are no crystallographic phase transformations that occur at the same temperature. No way, never. So that brings us to the alternative, which is what? AB is undergoing the crystallographic phase transformation. And because AB sits in the middle of the diagram, whatever it's adjacent to is affected by that phase transformation. So in the case of the diagram on the left here, A is here. Now why don't you just picture this and extend it over to here to another component, another phase, C. Right? And that would mean that phase transformation line would continue across to C, because whatever straddles the line has to be incorporated. But when the phase is on the edge of a diagram, it straddles in only one direction. You can visualize it straddling over here with another larger system, but we don't need to because that's the end member. But when we have it in the middle of the diagram, as over here, everything associated with it is going to be affected. Some of you are going to screw this up. I'm going to give you this to you on the final exam, and you're going to screw it up because you didn't pay attention or you didn't think about it. But everything I'm going to teach you in this class is totally logical. And it is logical to say, well, if I've got a phase, anything in contact with this phase is going to be affected. So if the diagram has an intermediate phase undergoing a CPT, whatever's on both sides will be affected. But if it happens, it's on the edge of the diagram, well, we can show only one side, but whatever might happen on the other, we just don't show. Still the same principle. Some of you are going to screw it up. Okay, so this is a crystallographic phase transformation. So now we've got eutectic, peritectic, eutectoid, peritectoid, melting point, crystallographic phase transformation. 6 invariant points. Who likes to eat salads in here? Raise your hand if you like to eat salads. Bullshit. Come on. You're all meat eaters, are you? You hate salads? I'm going to try it again. Who likes to eat salads? We've got a very few hands. That's more interesting than anything else? Tabbouleh. What do you put in the tabbouleh? Liquids. Lime juice. Anything else? Sorry? Some weird guy raised his hand. Where are you? What do you put on it to make it more interesting? Like what? Well, what kind of dressings? Balsamic. What's balsamic? What's the generic name for balsamic? Vinegar. You know what vinegar is? It's an acid. Anything else besides balsamics? Oil, olive oil. There you go. So oil and vinegar, right? Do they like each other? No. What do they do when you mix those two together? They separate, don't they? So what you have there is an immiscible liquid. Two immiscible liquids, right? Now, if you were to put ethanol and water on your salad, it would taste terrible, but it would be a homogeneous liquid, wouldn't it? Okay, but you go the hard route. You want oil and vinegar, and they're immiscible liquids. Okay, so if we can have immiscible liquids at room temperature, why can't we have them at high temperature? Okay. So what have I got in the upper part of this diagram? What's in the upper part of the diagram? What do I have? What kind of liquid? What kind of liquid do I have where L is? A homogeneous liquid. One phase. Okay, one phase. What do I have in the left-hand triangle? A plus L. What do I have right below that? What's right below that? A plus L. Wait a minute. Didn't we just go through this exercise to say how can we have two phase fields saying the same thing? That's totally illogical. But there's a difference between that one and this one. What is it? What's the difference between that last example and this one? This one has what?
Liquid and solid, whereas the other one had.
Well, that's true, but whether it's this liquid, solid, that's not really the issue. What is the issue? Have you picked that out? Anybody? Sorry? What about the liquidus curves? What are they? Are they the same? Are they different? Are the liquids different? Is that a yes? Is that a no? Or is it I'm not sure? Or is it I'm just afraid to give an answer? Who thinks the liquids are different? Raise your hand. Who doesn't think the liquids are different? Who doesn't know? Okay. So we got to know. That liquidus surface right there it represents what? What does that liquidus surface represent? We did it yesterday. What was it? What does it represent? There's two possible answers. One is it's where below we have liquid and solid and above it's all liquid, but that's not the answer I'm looking for. I'm looking for the other answer. What is it? Somebody mumbled, it sounded right. What was the mumble?
Saltiness?
No, that's not the solvus. It's a solubility limit. Solubility limit of A in the liquid. I emphasized that yesterday. You should have known that. What's this liquidus surface? Is that a solubility limit of A in liquid? Of course it is. Are they the same curves? No, they're not. So we're talking about different liquids. That's why I have two phase fields with the same names, because the liquids are different. But with the rectangular one, there was absolutely no difference between the two. So I had to have something else. So liquids change, different solubility limits as a function of temperature. What do I have in the right-hand triangle here? L plus B, and in the rectangle on the bottom? Okay, now you remember the way we identify these things is what's on the two sides of the phase field. So what's in that dome on top? L plus L? Would it be L1 plus L2? What about L3 plus L4? It doesn't matter. Trick question. I ask trick questions all the time. Two liquids, oil and vinegar. This is called a miscibility gap. Two liquids that don't like each other. These can be very important because the interfaces can be nucleation sites for recrystallization. Metallurgists use this all the time. This temperature right here where we have the onset is 1 to note, and this right here, top of the dome. In principle, at the top of that dome, I've actually got three liquids in equilibrium. Two liquids from the dome and the one outside of it. But as I said, we're never really on the lines. We're either slightly below or slightly above. But if we did go right on the lines, I'd actually have three liquids. That top of the dome is called a consolute point. And the temperature right there is the temperature that defines another invariant point. That's called a monotectic. Now, when we had a eutectic and a paratectic, we could plot them on the liquidus surface. But you'll notice with the crystallographic phase transformation, there is no point, the whole line, so it's a temperature. And so we had eutectoids and paratectoids that were lines, they weren't specific points. They're below the liquidus surface. I can't draw them on the liquidus surface. Same thing here. We do not have a monotectic point, even though I'm on a liquidus surface, because I've got two liquids, and so at the bottom of that dome is not one temperature, not one composition. So it's a monotectic temperature. So we don't refer to a monotectic point. We don't have that. Okay, so this is known as a miscibility gap. It's just two immiscible liquids. Now, in some rare instances, I can have an intermediate phase that when we heat it up, it doesn't actually melt congruently or incongruently. It turns into two liquids. This is called asyntectic. I dare say that if you go looking around for a syntactic, you're going to have a hard time finding it. It's not very common, but I give you a full package here of all the concepts. Okay? So now we have eutectics, paratectics, melting points, eutectoids, paratectoids, crystallographic phase transformations, monotectics, and syntectics. 8 invariant points now, for which you are responsible. Because on the final exam, I often ask you to identify the locations of the invariant points and tell me what they are. So wherever you have one on the liquidus surface, you put a little number or letter there. And then when it's below the liquidus or it's one of the ones at a temperature, you just put it on the line and then you give it a name. That tells me you learned this stuff. Yes?
Could you explain syntax again?
Okay, upon eating. All right. He's asked me to explain a syntactic. Now I want you to reset your brain. I want you to think, what does the diagram tell me? What can I read from the diagram? Because that's what this class is all about. So you start at room temperature, you need composition AB. And when you heat AB up, what happens to it? It gets heated up. Yeah, and when we go above the syntactic temperature, right here, what happens to it? F. So AB, arrow, heat, 2 liquids. So the diagram tells you that. You just have to think a little bit about how to interpret this. So each one of the diagrams tells you what you might be able to get from it if you heat or cool, or just look at it more globally. All right, well, why don't you take a break for 5 minutes? He's got the class roll.
You never made a custom.
How the offline beta here said that these are not, this doesn't represent the solid phase, but why are you using different?
Sorry?
Why are you using alpha and beta for these phases, although they are not representing solid phase? Solid solution.
Different crystallographic structure?
So they are actually, why do we can use different letter then, do we?
You can call it whatever you want, as long as you recognize it. It's a crystallographic phase transfer. Alpha A and beta A is a very common way of doing it.
Okay, I got it. Because, alpha and beta, we usually use it for the solid solution. So maybe some people might
You can call it whatever you want.
Yeah, hi. Is just to clarify, is the color solute point varying point? Yes, it is. Synthetic and synthetic temperature?
The temperature.
Oh,
Yes.
so, but you still count that as invariant?
Yes, yes, they're invariant points.
Oh, so the
They're invariant point temperature.
Okay.
Yeah. But I'll clarify that.
Okay. All right. Thank you.
Yes.
Oh, sorry. No. I just asked.
Yeah.
I wasn't sure.
About it.
What exactly is it?
Liquids that don't mix. Oil and vinegar.
Alright.
That's correct.
And there's no point.
That's right. Yeah.
I just about this part. I think you need by the alpha AB, now beta AB for this one.
You do, but you put it afterwards. It usually goes before. No, you screwed this up.
Oh, so it's
Beta AB.
Yeah, but why? Because it's like at the beginning you said it should be like either A or
you
B.
can call them anything you want.
Oh, so we can call it anything.
Call it anything you want. Crystallographic change. So that's alpha and beta. You can call that alpha and beta too, but they're both. That's a solid solution. That's a crystallographic. It's just a different way of calling things.
Why do alpha is like that? Not alpha.
No. AB's undergoing the phase transformation.
Oh, so
You
so
put this in the wrong
so
here.
in this one's only AB goes the crystallographic phase, but this one's only A goes like so it's different.
I mean, why?
Like she wants to ask why not you write the for the why not A and B separately go in crystallographic phase transformation?
We use Greek letters for solid solutions and for crystallographic phase transformation.
Like solid.
I'll try to clarify that. Okay. That's right. That's correct. Because I drew it that way. AB is undergoing the crystallographic phase transformation. Over here, that's the one. So you put it right there. That's both sides. AB down there. This would be, this is like AB down there, and it goes on both sides, but there's nothing over here. Right. Everything is. Yeah?
Just for clarification, with the paratectoid and the eutectoid, they're all temperatures. It's about temperature.
All right. Let's get going. I had a whole bunch of questions there, which clarifies some unclarity. Point number one. Those of you who are confused about alpha and beta. We use alpha and beta for two purposes. One purpose is to show a solid solution. So So I can call an A solid solution alpha and a B solid solution beta. That's what I did yesterday. Today, I showed we also use Greek letters for crystallographic phase transformations. So the low temperature phase is alpha, the next higher in temperature is beta, the next is gamma, the next is delta, the next is epsilon. Okay, so we have two ways that we use Greek letters in here. One's for solid solution, the other's for crystallographic form. If I use it as a crystallographic form, it does not imply there's a solid solution. That is not the case. It's just another way of using Greek letters. The other point came across was that when I listed the invariant points, I should have told you also that the monotectic and the syntectic were invariant points, and the constitutive point, well, that's unique as well. So that's also an invariant point. Not very important, but it is an invariant point. We can't move it without making phases appear or disappear. At that constitutive point, I told you I got three liquids, but only right there. If I move anywhere off of it, I have 1, 2, or 1. And I think there was something else. Yeah, I need to reiterate here on these crystallographic phase transformations. If you have a phase that's undergoing a crystallographic phase transformation, anything adjacent to it is going to be affected. So when that phase is in the middle of the diagram, I've got two phases adjacent, two phase fields adjacent. But when that's on the edge of a diagram, I have only one that's on show. There's another one there, but it's not on show. So we have it only coming out of the side. And the fact that I was asked this question tells me I'm correct. Some of you are going to screw it up because it didn't sink in. You're always affecting both sides, but if it's on the edge of a diagram, there's only half of it to be shown. Okay? That's how you know if it's coming in or if it's in the middle. So here's a couple of other variants. But I think before I do those, I better do the simpler one. This is a very common shape that we see in diagrams. So let's have a look at what we have. What's right here? That's a solid solution, and we're going to call it what? Alpha. What do I have up here? What kind of liquid? Homogeneous liquid. What do I have here? What do I have here? Lower right-hand corner, what do I have? Should be obvious. Just use your logic. What is it? What? Somebody say alpha? Did you say alpha? You're close, but you're totally bass-backwards. What was the answer? Is that not a homogeneity region bounded by curves? Yes? Just like alpha, just doesn't look like alpha, but it's the same thing. It comes in out of the diagram. It's a region. It's an irregularly shaped region. It's a solid solution. What is this? What is that point? Right down here. What? Melting point of B. So what's this? Which one is it? Okay. What's this thing? This one's a little tougher. This is not one that you might just automatically say, oh yeah, it's obvious. Anybody want to have a shot at what you think it might be? Is it on the liquidus surface? Does it stand to reason it's an invariant point? It better be. If I've got an inflection on the liquidus surface, I guarantee you that is an invariant point or an invariant point temperature. Always. So what's happening? I've got a horizontal line. What are the phases on the horizontal line? I have alpha here, I have liquid here. What do I have right there? What is it? What do you reckon? Who doesn't know the answer, raise your hand. Raise your hands proudly. Be proud of your ignorance. Okay, so your hand's not up. What's the answer? Late hand. Okay, let's try it again. Hands up if you don't know the answer, because if you don't raise your hand, I'm going to pick on you. Anybody not got his hand up? Raise your hand if your hand's not up. Okay. You know the answer.
Would it be the paratectic, at least at that point where beta is solid?
Okay, well that's not the question I asked. What is the question I asked? What's that last point on that horizontal line? What is it? What's that point right there? It's beta. It's obviously beta, because the solid solution region of beta sweeps up there and it hits that line. Wasn't that obvious? Maybe it's obvious now. Okay, and then you came up with another comment. You mentioned this word paratectic. And on what basis do you make that statement?
Because at the point where beta is, we've got one solid.
Well, wait a minute. You didn't know that was beta, but now you're saying it is. So did you know or not?
Wasn't sure. It's a very
Wasn't
thing.
sure. Okay. All right, so when beta hits, what happens?
You have one solid going to a different solid plus liquid.
That's right. So solid 1, beta, goes to solid 2, alpha, plus liquid, and that is a paratectic reaction. So she had the right invariant point, but wasn't willing to gamble that that was beta. And yet, time and time again, all the studies about people guessing on exams demonstrates your first guess is probably more likely to be correct than after thinking about it. So this is beta upon heating, goes to alpha plus liquid, and that's solid 1, goes to solid 2 plus liquid, and that's a paratectic reaction. This is really obvious. But the last time I drew a paratectic, I had a vertical line, a stoichiometric phase. But now I've got a solid solution that's undergoing a paratectic reaction, aren't I? So what? It's still a unique composition. All right, so now my question is this. Is B congruently melting or incongruently melting? Is B congruently or incongruently melting? Raise your hand if you don't know the answer. Raise your hand if you do know the answer. Okay. Or you Now there's an important message here. It is extremely important for you to read the exam question very carefully, because I phrase everything very specifically. So read the question before you start to answer. Hence, listen to the question. Okay? What she did is she broadened the concept of the question to beta, but my question was specifically about B. And she says B is congruently melting, and that's correct, because B is the ends member, is a unique composition, and by definition it must be congruently melting because it's on the edge of the diagram. Now to the point, is beta congruently melting or incongruently melting?
Take one composition of beta and bring it up to a melting point because you're going to start on the other side.
Made it much more complex. This is a no-brainer answer. Of course beta is incongruently melting because we just showed it decomposes paratechnically. You don't have to worry about the whole range of compositions. What you worry about is that invariant point. And beta is paratechnic, so it's incongruently melting. So you made it unnecessarily complicated. And here's another clue about the exams. Don't try to impress me with your knowledge. Just give me the answer. I got to grade a shitload of exams in here. And I don't want to read stuff. You either know it or you don't. It's either right or it's wrong. So just give me the answer short and sweet. And this one is a good example. Beta goes to alpha plus L, paratectic, incongruently melting. However, her answer does bring up another issue. What if I'm not at that unique composition? Is beta still incongruently melting? Of course it is. Because beta is beta, it's a solid solution. As soon as you dissolve a little bit of A and B, you changed it from congruent to incongruent. Doesn't matter how much A you have in there, it's still incongruently melting because you cannot go up in temperature and go from a solid to a liquid of the same composition, can you? Let's do it. Here's your composition right here. I heat it up. I go above the line. Did I transform from a solid to a liquid of the same composition? No, I did not. I transformed to this solid and this liquid. Incongruent melting. So see, that answers your question, but you really don't need to logic that out. Just look at that invariant point. It's paratectic, it's all paratectic. All right, so here we have a slight variation of an invariant point simply because it's incongruently melting. Well, it's a solid solution, I should say. Okay, so then we go back to what I drew here. And you can see we've got something similar on the right-hand side. So what have I got in this region right here? What is that? Okay, so what have I got in this region? So what is this invariant point here? Melting point. So I'm now going into a liquid region. Who said melting point? Raise your hand. No, it was a male voice. Who said melting point? You said that's a melting point. Okay, well how about I give you a hint and I put liquid up here. Now would you call that a melting point? Where is the melting point? Above that. So what is this thing down here? What's that thing lower down? What is that? You tell me. We covered it. Terrible guess. I'll give you a hint. It's got 3 letters. You can fuck off if you get it wrong. It's like having phase transformation, isn't it? So, wait a minute. Alpha, beta crystallographic, alpha, beta solid solutions. Holy cow. What do? Simple. Now I'm going to call them 1 and 2. You can call anything you want. Doesn't matter, as long as you signal to me what they are. Okay, I got a crystallographic phase transformation and 2 solid solutions to boot. So, beta 1, when we hit this temperature right here, goes to alpha plus beta 2. So what is that invariant point? It's a what? A paratectoid, an all-solid analog of a paratectic. It's subsolids. Okay. So, would I call that the paratectic point? No, there is no paratectic point. It's a paratectoid temperature. Okay, this, what is that? What is that point right there? You should know this. Yep. A eutectic. Who didn't know the answer to that? Raise your hand. Raise your hand if you didn't know the answer. So how come people didn't volunteer? Do I have a liquid going to 2 solids? Isn't that the definition of eutectic? Who cares if it's way up here or way down there? It doesn't matter. It's still liquid to 2 solids. It's a eutectic. What's that? What's that? What is it? Crystallographic phase transformation. It's a horizontal line that comes out of the edge. So that's alpha A to beta A. What's that? They do happen occasionally. What is it? It's a crystallographic phase transformation that changes temperature depending on how much B you have dissolved in it. Okay, you see that sometimes too. So there's another one. So alpha, beta, gamma. There's a confusing one for you. Or alpha 1, 2, and 3. Who cares? I don't care what you call it. How many invariant points do I have? How many? I see lots of fingers. Fortunately, none of these. How many? How many invariant points? 3? 6? Who thinks there's 6? Who thinks there's 5? Who thinks there's 7? Let's count them. 1, 2, 3, 4, 5, 6, 7. Oh, you missed one, whatever that was. Okay? 7 invariant points. We have a eutectoid, a eutectic and a paratectoid. Okay, let's look at this other diagram. What's in here? What's there? What is in that homogeneity region? Somebody want to tell me? Beta. What's in this homogeneity region? Think before you answer. Alpha 1. So that must make this alpha 2. And this, what is that? And this one? And what's this? Eutectic. What is that? Eutectoid, isn't it? Alpha 2 goes to alpha 1 plus must be B for beta. That's correct. So that's eutectoid. Can I identify a eutectoid point? Can I? There is actually a eutectoid point here. We don't normally think of it, but it is. So if that's a eutectoid point, that would suggest that one of these might be a paratectoid point as well. But the problem is, which one's which? You can't tell. So normally we don't think of eutectoid points, but in this case it's pretty obvious. For paratectoid and eutectoid points, the temperatures. But in this case it's obvious, there is a eutectoid point. But don't worry, you don't need to know that. It's just the temperature that counts. All right, so when we lay on solid solutions, it changes the appearance of some of these things. But if you know the principles, it's really easy to figure them out. But you have to know the basics. And the basics are not that complicated. Because you're about 80% of the way through the class now of what you need to know. Yeah?
Could you just explain why that's alpha 2?
Alpha 2.
Yes.
Okay. What's this point? Crystallographic phase transformation. Of what going to what? Isn't that alpha 1 goes to alpha 2? Yeah? And that means as we dissolve B into it, the transformation temperature drops, doesn't it? Okay? Suppose that phase transformation is very bad for us. It causes structural destabilization, and we don't want it. So that tells me that any impurities of B, when I process A, are really critical because they're going to drop my transformation temperature. So I've got to be very careful to exclude B from my impurities. Now turn it around. Suppose that phase transformation is piezoelectric, and I'd like to access that, use it as a thermal switch. So I reach a temperature, kicks in the phase transformation, and it does what? That's a reactive material, responsive material. So I can leverage that by choosing the exact right composition, so it switches at the temperature I want, and so I've got a thermal switch which is specifically designed for that composition, or through that composition. Okay. So if you know how to read these things and know how to make materials accordingly, you can get a lot of benefit out of these diagrams. All right, so that's a couple more examples to show you. How about that? Do that. Start there. So, better label this. What's up top? What's in the lens below it? That must be solid solution. So what's going on here? Speculate. What's in the middle of that dome? Middle of that dome. What's in the middle? No, it's not. it's another solid solution. So in these, I have two solid solutions, SS1 plus SS2. And this occurs very commonly in metallurgical systems. This is called a superlattice. Does anybody know what a superlattice is? Have you had this yet? No? Raise your hand if you've not heard what a superlattice is. Okay. You got a crystal structure. This is going to be a solid solution in the system gold, copper. There are three superlattices in this system. Gold and copper like each other. They form a complete solid solution. If you heat treat it, what happens is, within the lattice of the solid solution, another sublattice forms up. That's the superlattice. So there's ordering within the lattice. And there's three different ways to order them depending on the composition. So it's a lattice within a lattice. Forms usually upon heat treatment, and you can imagine what that would do to the properties. Now you've got something totally different from your average solid solution. Okay, so that's what a superlattice is, and this is what the phase diagram does when you have a superlattice. So there's a region where you've actually got two superlattices in existence, and then there's another region where all you have is this new superlattice, and that's what we have shown here. Okay? And if you want, you could call that a consolute point. I don't know if that's what they call it, but that's effectively what it is. So we have three solid solutions present at one temperature and composition. Then we have something a little bit different. You'll see this occasionally. This is called a second order phase transformation. Second order phase transformation. Now when we have a phase transformation, as in melting or solidification or volatilization, or a crystallographic phase change, these are all phase transformations from one state to another. And every time you have that, you generate something. What is it you generate? You guys all have thermodynamics. What do you generate? When you have a phase transformation, without exception, what do you have? Did you get this in thermo? Sorry? A rearrangement of energy, lose it or gain it. And what's that called? That gain or loss of energy. It's got a name. It's called a latent heat. Oh, you have heard it. Okay, latent heat. It's either exothermic or endothermic. It's exothermic, it's going to a lower energy. If it's endothermic, it's going to a higher energy. Okay, there's a latent heat. That's a first order phase transformation. That's the norm. But not always. We also have phase transformations where there's no latent heat. And that's called a second order phase transformation. So here we have solid solution 1 and solid solution 2. And it's just a rearrangement, and there's no latent heat associated with it. So you see occasionally a diagram that looks like that, and you go, how does that happen? Because right now I haven't told you one of the things that you might have noticed in these phase diagrams. So I'm going to go in that direction now. How many phases do I have? in that phase field? How many? How many? Hold up your finger. How many fingers? How many do I have in that triangle? How many phases present? 6? Phases. How many phases? Not how many invariant points. How many phases? 2. That's why you can do 2 fingers. How many do I have here? How many here? How many here? Here? Well, how many? How many? How many? How many? Do you see a pattern there? How many do I have here? How many here? How many? How many? How many? Do you see a pattern there? Okay, remember this. In binary systems, they always alternate. 1, 2, 1, 2. If you don't have that, you screwed up. But we have an exception. It's the exception I just showed you with the second order phase transformation. Something illogical happened. But this is nature. Okay, so 1, 2, 1, 2 always. And this will help you get the diagram right, because some of you will have trouble visualizing, is that a solid solution homogeneity region or something else? And this will help you figure it out, because then just go somewhere else in the diagram and go, all right, there's a vertical line, that's definitely 1, 2, and then, 1, that's got to be a homogeneity region. So you can figure it out if you remember that. Okay, so that's the 1, 2, 1 bit that you need to know. Now this is my favorite of all invariant points because it's called a degenerate. Okay. And it tells you that the liquidus surface just sweeps down to B from A. In reality, what this is this. It's still really a eutectic, but the problem is the eutectic is so close to the edge of the diagram that we can't actually detect it. But it's actually a eutectic. But when it goes so close that we can't tell, we call it a degenerate eutectic. In some of the older books, they actually call it a monotectic, because people are making up names. But it's properly called a degenerate eutectic. All right. Here's another slight variant. How many phases do I have here? How many do I have here? So how many must I have here? All right, so we're going to call that alpha, we're going to call that beta, and we're going to call that gamma. All right, so I've got a solid solution sitting here only at high temperatures. and in the middle of the phase diagram. And up to now, all my solid solutions, I came off of the sides. Okay? And these solid solutions are called primary solid solutions, and as you might guess, that one is called a secondary solid solution. It's not really important, but it's a term you might come across, so I introduce it to you. So tell me, gamma, it's got some invariant points associated with it. What are they? What are the invariant points? Upon heating, what invariant point does it undergo? What kind of invariant point reaction does gamma undergo? Upon heating, gamma is heated. What invariant point does it undergo? Raise your hand if you don't know the answer to the question. Okay? Let's work it out. There's the relevant invariant point. So I've got alpha on one side, gamma there, and liquid there. And upon heating gamma, gamma goes to alpha plus liquid. And what kind of invariant point is that? Paratectic. Not a paratectoid. There's a liquid there. Oids are all solid analogs. It's the top of the diagram. It's kind of a given that it's going to be an ick, not an oid. This one. Upon cooling of gamma, what invariant point does that involve? Gamma goes to alpha plus beta. It's eutectoid. Okay? What's this? I've got another inflection. What is that? This is the kind of question I like to ask on exams. This is a trick question. It's precisely nothing. It's irrelevant. It happens to be the temperature at which a eutectic occurs, but it's just one of the end members. There's no invariant point associated with gamma per se. Gamma is just what forms from the liquid. Liquid goes to gamma plus beta. It's not an invariant point related to gamma. Okay? So that's a trick question. If I asked you to identify the invariant points with the three inflections around gamma, and the students who don't understand are going to be working really hard to get three invariant points, and it ain't going to happen because there is no invariant point for the one. And I often ask questions like that. You go looking for something that's not there. And another point is that if I put 5 points on a question, it doesn't mean there's 5 answers. There might actually be 6 or 4. The numbers do not correlate. Okay, so scrub that one from your minds too. Okay, so there's a secondary solid solution. All right? Here's something that's a little different. You could say, oh, that's a second order phase transformation. But in this case, it's not. What that is metastable immiscibility. Now this is cheating a little bit because it's not at equilibrium, it's metastable. So what happens is that two-liquid immiscibility gap is retained upon cooling. So we've frozen in the liquid microstructure, and we end up with a phase assemblage of frozen amorphous liquids. Although it should be crystalline, it should be A and B, but it's not. It's frozen in two liquids. So that's a metastable miscibility gap. Okay, so sometimes you see that, and you'll pick that because there's a miscibility gap and then a matching one down underneath. That's weird. Before, I had a miscibility gap going right into the liquid, but now I've got a two-phase region in there of, oh my gosh, 3 liquids? How does that work? That's impossible. I can have 3 phases in a binary system only at a point. I can't have it in a region. So that's not a two-phase region. What that's called is a spinodal decomposition. Or a spinodal, sometimes I just use that term. Have you had this concept, a spinode? Yes or no? Okay, well this is what a lot of metallurgical systems have. And what a spinode is when a material can't make up its mind. It can't decide if it's going to be immiscible or miscible. And in that two-phase region there, it's kind of fluctuating between the two, and it's neither one. It's just kind of in the between state. And that spinodal decomposition is very important to metallurgists because it also helps you recrystallize metals. So that can be very important to a metallurgical system. It's not very important in ceramic systems, but in metallurgical systems it is. Okay, so that's a spinode there. And we have some terminology here. So we have a binode here, and that's the spinode inside. Okay? We can also bring it down and put it to solids. And so you've got spinodal decomposition in the solid state, and that's when it really becomes important, because the metallurgists cast, and then they have a solid, and they do a heat treatment. And if you're in that composition and it's kind of fluctuating around, it helps get things to happen. Okay, so that's a solid equivalent of the spinode. All right, let's have a look at this one. You've got a phase, I don't know, A4B3. A4B3. I'm going to cool it down. Is it congruently melting or incongruently melting? Is A4B3 congruent or incongruent? Congruently melting. I go from a solid to a liquid of the same composition. I'm going to cool it down. So, upon cooling, solid 1 forms what? What happens when I cool down? What do I get? What are my reaction products, or my invariant point reaction products? What are they? A and L. Ah. Huh. A paratectic, you have that reaction upon heating. But here, I've got it upon cooling. Ah, what a bastard. And not too surprisingly, this is called an inverse paratectic. And a whole lot of phase equilibrium books forget about it. But I don't, because you get the whole package. Inverse paratectic. It is a paratectic reaction, but instead of on heating, it's on cooling. All right? So that's pretty simple stuff. All right, so I've got a solid solution, but inside that solid solution, I've got a whole monotectic package going on there. So this is called a monotectoid. And I can almost guarantee you're not going to find that in any books. Okay, so it's an all-solid equivalent of a monotectic. But instead of having two liquids, I've got two solid solutions in equilibrium. And there is, of course, a consolute point where there's three of them present. So, invariant points. My goodness, what do we have? Eutectic, paratectic, melting point, eutectoid, paratectoid, monotectic, syntectic, monotectoid. We could, in principle, have a syntectoid as well. Never seen it, but it could happen. Crystallographic phase transformation. What else have I got? What other invariant points? Degenerate eutectic? Yeah. Well, a consolute point, yes. What else? Inverse paratectic? Yeah. Okay, so there's a slew of them here, right? You now know all the invariant points. Okay? Not that much to know. A lot of them are analogs, X and oids. Not too bad. Right? You've also seen most of the variants of the binary phase diagram. I've given you really simple examples, but if you use those as building blocks and just shove them together as multiples in a binary diagram, that's it. That's what you need to know. So, with the exception of some microstructural considerations, I've taught you almost everything you need to know for this class in 4 hours. And I gave you 15 minutes of harangue yesterday on towing the line and trying to learn. And you had 10 minutes of breaks